In this video I take a fairly comprehensive look at the advanced chemistry of alcohols. You could, however, use it as a revision source by scanning through the video and selecting out and watching particular elements of it. Let's take a quick overview of what I cover here. I'll take a look at the reaction of alcohols in combustion reactions, both complete and incomplete combustion. I'll look at its reaction with chlorinating agents, both phosphorus pentachloride, PCl5, and thionyl chloride, SOCl2. I look then at its reaction, or the reaction of alcohols with sodium, specifically ethanol with sodium to form sodium ethoxide and hydrogen. I'll take a look at the reaction of alcohols with hydrogen bromide in nucleophilic substitution. I look at the esterification reaction, where alcohols react with a carboxylic acid to form an ester, and also forming esters by reaction with acyl chlorides such as ethanoyl chloride. I look at the use of the so-called iodoform reaction or haloform reaction to identify certain alcohol groups or certain types of alcohol, where we use iodine and sodium hydroxide. And I'll finish by taking a look at the use of phosphoric acid to bring about an elimination reaction where water is eliminated from the alcohol to form an alkene. So let's make a start, and I begin with complete combustion of an alcohol. There's the equation for the complete combustion of ethanol, forming carbon dioxide, water, and of course energy. Let's look at the combustion of three alcohols. On the left there I have ethanol, in the middle butanol, and there hexanol. So the number of carbons is increasing as we go from left to right. And where the alcohol doesn't continue to burn on its own, I can use some cotton. So let me set these on fire. First the ethanol, and you'll see it burns with a clean yellow flame. More difficult to get the butanol to ignite, and indeed the hexanol. So again, I'm going to use some cotton-like material here. It's being used as a wick to keep the alcohol burning. So I'll now ignite the cotton, and it'll be the alcohol in the cotton essentially that's burning. And you can see that all of them are burning with yellow flames, with relatively little, if any, black smoke. And these combustion reactions produce heat. Let's take a look at the enthalpy change of this particular reaction, the combustion of ethanol. And you can see it has an enthalpy change of minus 1370 kilojoules per mole. Let's move on then to the use of PCl5 and SOCl2 to bring about nucleophilic substitution and form the corresponding alkyl halide or haloalkane. Clear liquid that boils at around 78 degrees centigrade. I'm going to transfer about 2 cubic centimeters of ethanol to a test tube and react it with phosphorus pentachloride. The OH group of the ethanol there, circled in red, will be substituted by a chlorine atom. So the PCl5 will behave as a chlorinating agent. This is an example of nucleophilic substitution. Here I have phosphorus pentachloride. You can see the safety symbols there. Contained within this plastic container I have a bottle, and in the bottle you'll see that I have a pale yellow solid, phosphorus pentachloride or phosphorus 5-chloride. This tends to smoke in air, as you can see, and if you bring in a reagent bottle containing concentrated ammonia, you can see that a white smoke forms. This is because the phosphorus pentachloride reacts with water vapor in the air, forming hydrogen chloride gas, which then reacts with the ammonia to form gaseous ammonium chloride, which sublimes to the solid ammonium chloride, a white solid. We use that as a test for the presence of HCl gas. So let's get this reaction underway. I'll put some of the phosphorus pentachloride solid in the second test tube here so that you can see better what's going on. So here's the pale yellow solid, phosphorus pentachloride. You can see I'm taking there about half a teaspoonful. Again, there's the equation, and you can see that it's nucleophilic substitution. The OH of the ethanol is replaced by a chlorine. We say the PCl5 is a good chlorinating agent. Look at the other products of the reaction. HCl will be formed as a gas, and also POCl3, phosphorus oxychloride. So watch now as I add the phosphorus pentachloride. You can see it's a very vigorous reaction. You can see that the liquid there, the ethanol, is boiling. And if I bring in the concentrated ammonia, you can see that a white smoke is produced, evidence that HCl gas is indeed produced. And there's the equation for the reaction that forms the white smoke. The HCl reacts with the NH3 from the reagent bottle, forming a white smoke of ammonium chloride. And then let's use an alternative chlorinating agent, thionyl chloride, formula SOCl2. We get the same organic product, chloroethane, and indeed we get HCl again. But the other product is sulfur dioxide, a poisonous acidic gas. So of course this should be done in a fume cupboard. In this video I take a look at the reaction of this chemical, a colourless clear liquid called thionyl chloride, formula SOCl2. It's an excellent chlorinating agent. Highly reactive, and in its reactions we get highly acidic HCl fumes produced, and worse still, sulfur dioxide, which is very poisonous, brings on attacks of asthma. So this is of course carried out in a fume cupboard. I've muted the sound of the fume cupboard here, but I can assure you the fume cupboard's going full tilt. And here I've got pure ethanol, or 99.5% ethanol, as methylated spirits or denatured alcohol contains contaminants. So in this instance we've got pure ethanol. So let me put a couple of cubic centimeters of 99.5% ethanol into a second test tube. And again you'll see that ethanol is a colourless clear liquid. There we go. That's the ethanol, C2H5OH. If I bring in an open bottle of ammonia, I can show you that at this stage we have no HCl in the atmosphere around the test tubes. No white smoke there. Now I'm going to add the ethanol to the thionyl chloride, and you'll see that the liquid mixture boils in a very exothermic reaction. Here we go. You can see the balanced equation. It forms chloroethane, HCl and SO2. Let me bring in again this open bottle of ammonia, and you can see indeed that we have white fumes, proving that HCl is a product of the reaction. Now SO2, which is also a product of the reaction, is a reducing agent, and it should reduce potassium permanganate solution, as you see in the equation here, from its +7 to its +5 oxidation state, which is colourless. So we go from purple to colourless. Just a test, a simple test being used to prove that a reducing agent is present here. In this instance it's sulfur dioxide. Moving on then to the next reaction, the reaction with sodium. And here you see the equation for the reaction of sodium with ethanol to form the salt sodium ethoxide and hydrogen gas. So here it's the OH bond of the alcohol that's breaking, and that's producing the hydrogen together with the ethoxide ion. And there's the salt, sodium ethoxide. In this video, I take a look at the reaction of sodium metal with ethanol. It appears white sodium when it's removed from the oil in which it's stored, but when you cut through it, you can see it's shiny there for a few seconds before it tarnishes again. So that's to say the metal is shiny grey, but when it reacts with chemicals in the atmosphere, including oxygen and water vapor, it appears white, mainly the oxide of sodium. So let me drop some of the sodium metal into ethanol in a boiling tube. First observation, it sinks. So sodium is more dense than ethanol. You'll probably have recalled that it's less dense than water, so it floats in water. The products of the reaction, a salt called sodium ethoxide and hydrogen gas. You can see a steady stream of bubbles there. Those are bubbles of hydrogen gas. Perhaps if we use a black background, you'll see the bubbles a little bit more clearly there. Let's take a look at what's happening in this reaction. So this is the structural formula or condensed structural formula of ethanol, and that OH bond breaks. The curly arrow shows that the 2 electrons of the OH bond both go on to the oxygen. So the oxygen will have an extra electron that had belonged to the hydrogen and will therefore have a negative charge, and that creates what's known as the ethoxide ion. So the alcohol is kind of behaving as an acid here, giving up a proton. So it's like a MASH reaction in that sense. A MASH reaction referring to a metal reacting with an acid to form a salt and hydrogen. And to balance the equation there, half a mole of hydrogen gas is produced. So we get a salt, sodium ethoxide, and it'll be dissolved in the ethanol that has not reacted. I have speeded the video up here. It did take, with that amount of sodium, approximately 5 minutes to fill the boiling tube with hydrogen gas. What I'd like to proceed to do then is to evaporate the ethanol off to prove that there is indeed a salt present dissolved in the ethanol. So here's the test tube where I'd reacted the sodium with ethanol. You can see a deposit actually at the bottom of the test tube there. So there's some sodium ethoxide already there. So I've poured out the solvent into an evaporating basin sitting on a hot water bath. Ethanol, of course, is flammable, so we need to keep that well away from the naked flame beneath the gauze there. So the water bath will provide enough energy to evaporate the solvent ethanol off, and we should be left then with a solid, which is the salt, sodium ethoxide. So you'll have the chance to see what it looks like. And as I'm sure you notice, the video has been speeded up, probably by about ×8. And we end up with what appears a pale yellow coloured solid. There we are. It's going from a brown colour to a pale yellow colour. And I added some water just to test the solubility of sodium ethoxide. And I was able to show that it does indeed dissolve to form a brown coloured solution. So sodium ethoxide, being ionic in nature, is soluble. And that's my look then at the reaction of sodium with ethanol to produce sodium ethoxide, an ionic solid soluble in water, and hydrogen gas. Now let's move on to nucleophilic substitution and the reaction of an alcohol with hydrogen bromide. Hydrogen bromide is unstable and is made in situ. That's to say, it's made there and then where it's needed. It's made typically by the reaction of potassium bromide with concentrated sulfuric acid. You see it forms HBr together with potassium hydrogen sulfate. The HBr then, having been made in situ, reacts with the alcohol to form the corresponding alkyl halide or haloalkane. We get bromoethane from ethanol and water. In the upcoming video, I take a look at the formation of 1-bromobutane from butene-1-ol. Again, primary alcohol to a primary alkyl halide.
You are looking here at a 100 cubic centimetre pear-shaped flask. The chemicals are undergoing reflux distillation. If you look here, you'll see there's a Liebig condenser. This is called reflux distillation, where the condenser is set in a vertical position. The rule is water should always be pumped uphill in a condenser, so the water is going in at the bottom and out at the top there. And in this pear-shaped flask, I am carrying out this nucleophilic substitution reaction, replacing the OH group in butene-1-ol with a bromine atom to form bromobutane. So this is the reaction in which I'm changing a primary alcohol, butene-1-ol, into a primary halogenoalkane, bromobutane. How did I do it? Well, I started by putting 6 grams of potassium bromide into the pear-shaped flask, and I dissolved it in 6 cubic centimetres of deionized water. I then very slowly added concentrated sulfuric acid, the same volume, 6 cubic centimetres. I added it slowly, a few drops at a time, shaking the flask all the time and keeping it cool in a beaker of cold water. The concentrated sulfuric acid will tend to char the butene-1-ol, literally breaking some of the molecules down, making the liquid go yellow or even brown in appearance. And I wanted to avoid that, so it was added slowly, keeping it cool all the time. Charring will obviously mean that you have less butene-1-ol to form the product that you look for, so it would reduce the yield of product. I then added just a pinch of anti-bumping granules to promote smooth boiling. As you heat any liquid, gases dissolved in the liquid will come out because solubility of gases in a liquid falls as temperature rises. So you'll see bubbles coming out. Those bubbles, if they come out all of a sudden, will cause bumping to take place, which is dangerous. It could force the Liebig condenser out there because of the sudden build-up in pressure. So the anti-bumping granules, just a pinch, plays a very important safety role here. It promotes smooth boiling. And you can see here I've got a relatively small flame and I'm refluxing for 30 minutes. You might just be able to see there, if we go in at the bottom of the condenser, you can see the rate at which it's dripping there. So gentle refluxing for 30 minutes. Now, what's the role of the potassium bromide and concentrated sulfuric acid? The concentrated sulfuric acid has a dual role here, but in the first instance, the concentrated sulfuric acid reacts with the potassium bromide to form hydrogen bromide as well as potassium hydrogen sulfate. We say that the hydrogen bromide is being made in situ, in situ, S-I-T-U. In situ is normally written in quotes. What it simply means is we're producing the HBr there and then in the flask. You can't make HBr and keep it in a bottle because it's unstable, so you've got to make it there and then, in situ. I said the concentrated sulfuric acid has 2 roles. The other role is, because it is a dehydrating agent, it helps improve the yield of products. How is that? Well, by removing water, which is a product in this reaction, as well as the bromobutane, it means that the reverse reaction can't take place. So the concentrated sulfuric acid, as well as reacting with the potassium bromide to make HBr in situ, it helps the yield of product by removing the water, which is a product in the reaction, and that prevents the reverse reaction. And I'm refluxing here the reactants for 30 minutes using a small Bunsen flame. Use a moderate flame. no sign of any distillate. What we collect from simple distillation is known as the distillate. Carbonate would also have done. Going to add that to the funnel. You notice some effervescence there. Calcium chloride comes in lumps like this. So I'll drop those in. And you shake it now and again for a period of about 5 minutes to dry the product.
So that was nucleophilic substitution, the formation of a haloalkane or alkyl halide from the corresponding alcohol, primary alcohol in that case. Next, let's take a look at esterification. Here we have the reaction of an alcohol with a carboxylic acid in the presence of the catalyst sulfuric acid. Reflux distillation is required. You can see that the products are an ester, in this case ethyl ethanoate from ethanoic acid and ethanol, plus water. The preparation and purification of ethyl ethanoate ester. This is what happens in the reaction between glacial ethanoic acid and ethanol. The H from the ethanol and the OH from the ethanoic acid produce water, and the other two parts of the molecules join to form the ester. The reaction is catalyzed by concentrated sulfuric acid. You probably don't need to know this, but this is the role of the acid. It provides hydrogen ions which protonate that OH group of the carboxyl group. That produces OH2 there at the bottom right with a positive charge on the oxygen, and the bond will split to give water. This is the setup used. It's called reflux distillation. We have a round bottom flask with a Liebig condenser fitted in a vertical position. Anti-bumping granules will be put in the round bottom flask to promote smooth boiling. Water goes in at the bottom and out at the top, and the reaction is got underway by adding the catalyst concentrated sulfuric acid slowly down through the condenser. That begins the reaction before any heat is supplied or heat is necessary. So that's the reflux distillation setup. It's important to note that this reaction is a reversible reaction. And the concentrated sulfuric acid, as well as being a catalyst, it's a dehydrating agent. And by removing the water, a product of the reaction, it prevents the reverse reaction and gives a higher yield of product. After refluxing for about 20 minutes, you're then ready to isolate the impure product, the ester. You still have anti-bumping granules in the round bottom flask. You change the apparatus for simple distillation like this. Got a collection arm there to collect the distillate into a conical flask. Again, you use a hot water bath. This improves safety given that the ethanol and the product, the ester, are both flammable. And you distill off about 2/3 of the mixture into the conical flask as the distillate. The ester at this stage is still impure, and you now proceed to carry out 3 different steps to purify the ester. The first is called washing, and this is done in a separating funnel like this. This is of course to remove any sulfuric acid that has distilled over with the ester into the flask. What you do is to add about 10 cubic centimeters of aqueous sodium carbonate at a time, and you'll get effervescence because CO2 is produced. The two reagents need to be shaken together because they are immiscible. And as you see here in the equation, a metal carbonate reacts with an acid to give a salt, water, and CO2. Further 10 cubic centimeter amounts of aqueous sodium carbonate will be added with shaking until no further effervescence is observed.
That means that the sulfuric acid has fully reacted and has been converted to the salt and water. The salt and water will form the lower layer, and the ester should be the upper layer. And of course, the carbon dioxide gas will escape. Now, even if you're patient and you allow the layers to fully separate, a little bit of water will be caught up in the ester layer, so the next stage is to dry the ester and remove that water. This is done using anhydrous sodium sulfate. So the ester is transferred to a small conical flask, anhydrous sodium sulfate solid is added, flask is stoppered, and then it's shaken for about 5 minutes to remove the water. And then finally, the ester is decanted out into a round bottom flask, anti-bumping granules are added, and the ester is redistilled. Ether is always formed in this reaction as well, and it distills off between about 35 and 40 degrees centigrade. The purified ester distills between 74 and 79, so that fraction is collected as the purified ester. That's it, the preparation and purification of ethyl ethanoate.
Alcohols will react much more vigorously with acyl chlorides to produce an ester together with HCl gas. In this reaction, you see ethanoyl chloride, CH3COCl, react with ethanol to form the same ester, ethyl ethanoate, together with HCl gas. No need for a catalyst nor for heating. You'll see in a moment that the reaction is extremely vigorous. So ethanol this time behaves as the nucleophile, and again it's a lone pair on the oxygen of the ethanol molecule. Here's the mechanism. We've replaced in the water molecule, so to speak, a H with CH2CH3 there, and that's carried forward into the product. So this time we get an ester produced instead, and it will have, of course, a fruity smell, and in addition we get HCl gas produced. So let's see that reaction. So I'm going to add some ethanol, and let's see what happens. After just a moment or two of delay, we get a very vigorous reaction. You can see the liquid mixture boiling and bubbling. And again, if I bring in an open reagent bottle of concentrated ammonia, we see the white smoke created, which is evidence that HCl is indeed a byproduct of the reaction. So the two products, ethyl ethanoate, an ester with a fruity smell, and hydrogen chloride gas. And the ester should be present in the test tube there. It is a colourless liquid, and it'll be there present with any unreacted reactant. Next, let me take a look at the iodoform test. It tests for alcohols that have this particular structural arrangement. That's to say the carbon to which the OH is attached also has both a methyl group, CH3, and a H attached to it. With such alcohols we get a positive test in the iodoform test. You'll see it's a three-stage process. In the first step, both iodine and sodium hydroxide are involved. In the next step, iodine is involved, and in the final step, hydroxide ions. Quite a lot going on here. First of all, the red curly arrow shows that the hydroxide ions deprotonate the OH group of the alcohol. That's to say the H of the OH leaves without its electron. It leaves as a hydrogen ion or as a proton, combining with the OH minus ions to form water. The two electrons of that OH bond, shown with the green curly arrow, are reassigned to form a pi bond between the C and the O. That produces a C double bond O in what is next formed. And the purple curly arrows there show that something else is happening. The I bond between the iodine atoms in the iodine molecule breaks heterolytically. That's to say both electrons go to the left-hand iodine, forming an I minus ion. Meanwhile, the two electrons of the CH bond there are reassigned to form a bond between the H and the I, giving us hydrogen iodide. And at this intermediate stage, you can see there that we have a carbonyl formed. If that OR group was a H atom, then we would have the aldehyde ethanol. So that means that ethanol will also give a positive iodoform reaction. If the OR group was an alkyl group, such as CH3 or C2H5, then we'd have a ketone. So that means certain ketones give a positive iodoform reaction, specifically ketones where the C double bond O is on the second carbon, 2 ons.
Let's look at the second stage then. You can see that the iodine is reacting to displace the H's, or substitute the H's of the CH3 group. Hence the need for a methyl group for the positive iodoform reaction. Look what's happening then in the third and final stage. You can see that that CC bond is breaking. You can see the role of the OH minus there, behaving as a nucleophile, attracted to the carbon, which will have a delta positive charge on it. That gives us that Ci3. There'll be a minus charge at that stage on the carbon because it's taken both electrons of the CC bond. Meanwhile, on the right there, with the OH going in, we'll have produced a carboxylic acid. But then we get the H leaving the OH of the carboxylic acid to give us CHI3 there, together with the ion of a carboxylic acid. So we will get the sodium salt of that particular carboxylic acid. If it had been, if OR for example had been a H, then we'd have sodium methanoate. If OR was CH3, then we would have sodium ethanoate. The key thing is that the CHI3 triiodomethane is a yellow solid with an antiseptic smell, and that's what we're looking for in the positive iodoform reaction. Let's look at that test. So let's get the test underway so that you can see what happens and where the test is positive and negative. So I'm going to begin with the ethanol, as you can see, and I'll take some in a second boiling tube. Normally we just take 1 or 2 cubic centimeters of the alcohol in a test tube, but for the purpose of this demonstration video I've taken a much larger volume. Now you add approximately 1.5 times as much of the 10% the 10% iodine dissolved in potassium iodide. So I'm going to more than double the volume in the boiling tube there. If I was doing it in a test tube, I'd take probably about a cubic centimeter of the alcohol and add several drops of the 10% iodine solution. Okay, the test will not get underway, as you saw from the equations a moment ago, until I add the sodium hydroxide. So let's do that. I'm going to add 2 molar sodium hydroxide, and recall how that reacts with the iodine to produce sodium iodate 1, NaIO, which behaves as an oxidizing agent. And that will oxidize the alcohol to the corresponding carbonyl compound. And what the procedure requires me to do here is to add the 2 molar aqueous sodium hydroxide in a slow dropwise fashion. I'm using a small syringe here for convenience. And I keep adding the sodium hydroxide until the brown color of the iodine disappears, or just disappears. So I'm going to add the sodium hydroxide and shake it. And you're aware then that the sodium hydroxide will react with the iodine, and from that reaction we'll create or produce sodium iodate 1, NaIO, which is a mild oxidizing agent. You can see the color fading there as the sodium hydroxide goes in. And the question is it simply going to fade and produce a colorless solution, which would be a negative test, or is it going to get lighter and brown and actually then produce a yellow precipitate triiodomethane that has an antiseptic smell? So let's see. So the brown color is fading as I continue to add the sodium hydroxide. So we're looking for one of 2 results. It is either going to go colorless and clear, or it's going to jump over to a yellow color and go cloudy as a fine yellow precipitate forms. And you can see
What we've got here is a fine yellow precipitate. This is a positive test because we have produced triiodomethane. In there is a fine yellow precipitate which you'll see at the end of the video when I filter it using vacuum filtration. So ethanol, which we would have expected from its structure, gives a positive iodoform test. In ethanol, you can see here we have a carbon that is bonded to an OH group and to a H and a methyl group. Those are the requirements for a positive iodoform reaction. So let's move on to the next alcohol, which is propan-1-ol. Consider the structure of propan-1-ol and whether or not you think it will give a positive iodoform reaction. So again, I'll take some propan-1-ol in a separate boiling tube. Much greater volume than one would use normally for these tests, just so that it shows up better on the camera. I'm going to add about 1.5 times as much of 10% iodine solution, dissolved potassium iodide. Note that iodine doesn't actually dissolve in water, but it dissolves in a dilute aqueous solution of potassium iodide. It actually goes into solution as the I3- ion, from which I2 can be liberated very quickly. Anyway, next I add the 2 molar aqueous sodium hydroxide. Again, I keep adding it with shaking until the brown color just disappears, and we're looking for one of two possible outcomes. It's either going to fade and fade and fade and eventually form a colorless clear solution like water, or it's going to jump over to a yellow color and become cloudy as a yellow precipitate forms inside, and that precipitate will have an antiseptic smell. Still a little bit brown, but watch what happens when it goes into the boiling water. You can already see there, I hope, that it's gone colorless and clear. That's a negative test. So with propan-1-ol, we have a negative result for the iodoform reaction. So we need to take a look at the structure again of propan-1-ol to see why we have a negative result. It must be the case that the carbon holding the OH group must have absent either the methyl group and or the hydrogen atom attached to it. So here's propan-1-ol. There's the key carbon in question that's attached to the OH. Well, it is indeed attached to a H, but you'll see it's not attached to CH3. It had an ethyl group instead of a methyl group, so that was the correct result, negative. Let's move on to the position isomer of propan-1-ol. That's propan-2-ol. So the position of the OH group on the 3-carbon chain is different. It's on the middle carbon rather than the outside carbon. So again, I've added my 10% iodine solution, and now I begin to add slowly with shaking the 2 molar sodium hydroxide solution. The brown color is fading, and we're looking for again one of two possible outcomes. And you can see already there that it's jumped over to that yellow color, yellow and cloudy, because we formed triiodomethane, known as iodoform. Pale yellow precipitate. I'm wafting the fumes towards my nose there, picking up the antiseptic smell. So why does propan-2-ol give a positive test? Let's look at the structure of propan-2-ol. There's it there. The OH is on the inside carbon. And does that inside carbon have attached to it both a H and a methyl group? Well, there's the H. And in fact, it has a methyl group either side. So you can see why it gave a positive iodoform reaction. Remember how the H there is removed in the oxidation reaction together with the H of the hydroxyl group. That happens during the oxidation stage. And then the H's of the methyl group are replaced with I's to give CI3. And then it decomposes with the hydroxide ions in the final step to create triiodomethane together with the sodium salt of a carboxylic acid. So here I've got the last one, butane 1-ol. Consider its structure and whether you expect this test to be positive or negative. So I've added about 1.5 times as much 10% iodine solution as alcohol, and I'm now adding 2 molar sodium hydroxide solution slowly with shaking. The butane 2-ol is a bit more viscous and takes a bit more shaking here. The colour is fading. Did need a bit more encouragement this to see whether it was going to turn into a colourless solution or instead produce a yellow precipitate. So keep watching here. The colour is fading. I did feel the need to use the hot water bath in this instance to encourage it. Still not completely clear whether it's going yellow or brown at this stage, but watch it as it sits now in the hot water bath. And I did add a good bit more sodium hydroxide to get a result. I needed either it to go colourless and clear, or I needed it to go yellow and cloudy. I wanted one or other result, so I kept adding sodium hydroxide and warming it in the water bath. In fact, I found I had to add even more sodium hydroxide to get one result or other. And at this stage I was convinced that it wasn't the yellow precipitate. Certainly no yellow precipitate there. And at the bottom you can see it has gone colourless and clear. Here's the structure of butane 1-ol. There's the carbon that's attached to the OH. You can see that it does have a H attached, but it doesn't have a methyl group. It has a propyl group instead, and that won't do. So that's why it was negative, exactly what one would have expected. So that's the ethanol. We had a positive test with that, and we had a positive test with a propane 2-ol there. We had a negative test with a propane 1-ol, and we had a negative test with the butane 1-ol. Let's take a look then finally at the precipitate. So here's a Buchner funnel and Buchner flask attached to a siphon pump which draws the air out of the flask. This is referred to as vacuum filtration or filtering under reduced pressure. Into the Buchner funnel I need to place a filter paper of an appropriate size to cover the holes. And before I pour the suspension in, I do need to wet the filter paper to make it stick down over the holes, otherwise the precipitate will go underneath and I don't want that. So it's wetted down now with the solvent, and we can now pour it in. You can see I haven't made a great job of there. There's still some solid left behind, some of the triiodomethane left behind there. And there's it there on the filter paper. That brings us then to the final reaction of alcohols that I'm looking at here. Dehydration using the catalyst phosphoric acid. Let me take a brief look at the steps in this reaction. I'm using propane 2-ol as my example of an alcohol. You can see the OH group is on carbon 2. So how does the phosphoric acid behave as a catalyst here? Well, in the first stage, the phosphoric acid protonates the OH group. That's to say, a hydrogen ion coming from the phosphoric acid protonates the OH group. Look how the lone pair, one of the lone pairs on the O of the OH group, is used to form effectively a dative bond with a hydrogen ion that's coming away from the phosphoric acid. The curly arrows help to track the movement of a pair of electrons. That's going to form this ion, which will be unstable, where we have a positive charge on the O there. But then the phosphoric acid in the second stage will do this. This time the bond between the O and the C will break, both electrons going on to the O. And that of course will give us water, H2O. The positive charge will have gone because the oxygen will no longer be sharing the two electrons with the carbon and will effectively be up an electron. And then look what's happening. One of the H's of an adjacent CH3 group goes away, leaving its electron behind, and those two electrons of the CH bond are reassigned to form a pi bond between the carbon atoms, giving us the carbon-carbon double bond. And equally importantly, to regenerate the catalyst, phosphoric acid, you can see that that H, or proton from the CH3 group, has gone back to complete the phosphoric acid molecule. We say the catalyst has been regenerated and is available to enter into the same process once again. So there you have my look at the main reactions of alcohols. Thanks for viewing.